Hey guys, this video is going to be about metabolism and energy. I'm going to start by sort of defining what metabolism means for us in biology. Metabolism is all the chemical processes that occur inside of an organism that helps maintain its life. So it's where we go from one type of energy to a usable form in a cell. This is how living organisms are going to be able to turn food, any energy from their environment into a usable form the cell can use, which is ATP. So I've got two pictures here. We've got a little flower soaking up the sun's rays, and we have a little deer who's munching on some grass. So there's actually two main processes that we talk about in metabolism. The first being photosynthesis, which is where a plant is going to take sunlight and turn it into sugars, which is why plants are at the base of the food chain. And then we have the process that we actually use as human beings, same as our little deer right here, is we have to eat food and break it down into a usable form. So we actually use cellular respiration to do that. Because basically all the food that you eat is useless to your cells unless it's turned into the quote-unquote cellular currency of ATP. Your body can use ATP. Sugars, it can't really use them unless it breaks it down into ATP. So one thing I do want to mention is that plants actually do both photosynthesis and cellular respiration. They build sugars using sunlight, and then they break those sugars down into ATP in their mitochondria. That's a big misconception that people kind of confuse, is they think that plants do photosynthesis and animals do cellular respiration, when in reality plants actually can do both of those things. So now let's take a look at the different types of energy that we have to focus on in biology. What is energy? Well, it's something that is a little abstract because we can't taste it or see it, but we can use it and we can convert it from one form to another. But essentially, energy is defined as something that allows us to do work, the ability to do work. So energy can come from a physical or chemical resource. So think up here we have our vehicle where you put gasoline in, which is a physical form of energy, which is fossil fuels, and then we can combust it inside of a car engine, and it allows the car to do work or to travel from point A to point B. Down here you can see we have a nuclear power plant, which is going to take uranium, and inside control rods it's actually going to use the energy that is emitted by uranium as it's broken down to heat and boil water, which is actually why you see steam coming out of the top of the nuclear power plant. And they use that steam to turn turbines, which will then power our homes or can be stored and used as electricity. So electricity that some people use in their homes could derive from a nuclear power plant. For the most part, we actually just use coal, especially here in Kentucky. So although these are really good examples of how we can manipulate different types of energy sources like uranium, gasoline, fossil fuels, I'm going to focus on biological systems for the most part, given this is biology. So I do want to make a note that in biological systems, our energy source is going to be sugars, fats, proteins, different types of food that we break down into ATP. So let's take a look at two major types of energy that we're going to focus on and use as we go through this metabolism unit. So first we have potential energy, or PE, and potential energy is defined as energy that is stored between bonds. More complex a molecule, the more bonds it has, the more potential energy. And it also can be defined by where an object is in space, which is a little bit weird to think about. So I'm going to give a couple examples. So on the left we have chemical energy, which is energy stored in chemical bonds between the atoms in a molecule. And then on the right, we have physical energy, which is more of position in space. And there's other examples of physical energy, but I'm going to focus on position just for biology. So let's take a look at chemical energy first. So here we have two molecules that we're going to be dealing a lot with in cellular respiration and photosynthesis. On the top, we have glucose, which is C6H12O6 as its formula. And on the bottom here, we have carbon dioxide, which is just CO2. Glucose is going to be a solid, which is a much more stable form. And carbon dioxide's a gas, much more chaotic, crazy, moving around the air. So we can look and see, obviously, glucose has got a lot more bonds and a lot more atoms in it. So this molecule actually has more potential energy, whereas carbon dioxide as a gas, and it also has just one carbon and two oxygen, is going to have a lot less potential energy. And this is going to come back when we talk about both cellular respiration and photosynthesis. You can also think about this in terms of complexity. So more potential energy usually means more complex, and less potential energy means less complex. And you can see that by the solid and gas as well. So let's look at the physical energy example. If you've ever watched Olympic diving, you've probably seen that they have platforms that look like this, where you have multiple levels that divers will dive off of depending on what tricks and skills they're going to be performing. So what I want to do is explain that up here, a little diver at the top will have more potential energy than a diver at the bottom. So diver A had to use a lot less energy to climb the stairs to get to this platform. So they have a much shorter distance between them and the ground. And because they use less energy to get to this platform, they have less potential energy than diver B up here, who had to climb all of those stairs to get to the top. So because diver B used their energy way more so to get all the way up here, probably a couple stories high, they have a lot more potential energy. And you can see that as diver A and B jump off, their kinetic energy that they actually will be kind of transforming their potential energy into as they jump off. Diver B is going to have a lot longer time in the air, and also is going to probably gain more speed as they reach the pool, whereas diver A is not. So that brings me to our next form of energy, which is indeed kinetic. Kinetic energy is defined as the energy of motion. The faster molecules are moving, the more kinetic energy they have. So in this case, kinetic energy and temperature are extremely linked, in that the hotter something gets, the faster the particles are going to move. And the cooler it gets, those particles will actually slow down until that particular substance is frozen. So that's why as you watch an ice cube melt, the particles in that ice cube are actually moving faster and faster. And it appears to your eyes as an ice cube melting into a liquid. And then if you heated that liquid up further, it would turn into water vapor, which is the most chaotic state of matter as a gas. So just know that temperature and kinetic energy are extremely linked. A lot of times potential energy can be converted into kinetic. You can see that as a roller coaster reaches the top of the hill, it is going to be released and it'll fall downhill into a more stable state, and it releases energy in the form of kinetic to get there, aka it is in motion. So the last part of this video, I'm going to talk about the laws that energy abides by, sort of like the laws of the universe, which are called the laws of thermodynamics. Thermo meaning heat, so heat will be related to these laws, as energy and heat are definitely going to go hand in hand. So the first law of thermodynamics is that energy cannot be created or destroyed. There is a finite amount of energy in our universe, and in our particular solar system, we rely on the energy that comes from our sun. Because no energy comes from nothing, everything has to have an energy source, whether you're looking big picture like our solar system or even smaller like each individual cell in your body. Everything has to have a source. All energy on Earth, we can trace it back to the sun. Even the fossil fuels that power our vehicles are going to have the sun as the ultimate source, meaning that dinosaurs ate plants that made food using sunlight. They died, they decomposed underground, compressed over millions of years, creating gasoline, coal, natural gas. So no matter what you look at, all of the items that you see in your house, at school, everything, its original source was actually the sun, including the energy that you use on a daily basis to power your own body. Our energy comes from the sun. We eat food. If you trace all of our food sources back, it goes to plants. Plants make food using sunlight. Solar radiation is going to come in to our planet from the sun. And it's actually a lot of energy does release off of our planet in the form of heat, which brings me to the next law of thermodynamics, in that every energy conversion leads to some sort of increase in disorder and heat and chaos in the universe. That randomness and chaos is actually called entropy, which is just the scientific word for everything in the universe is going to favor chaos, which is kind of abstract, but I'll give you guys a couple of examples. All matter will favor the gaseous state, and in order to not be in the gaseous state, energy has to go into a system. The second law of thermodynamics explains why if you don't put energy into something, it will quote unquote fall apart. The falling apart that you see is just something solid kind of degrading into a gaseous state over time. So think like an abandoned building. If you, as a person, stop putting energy into a building, it will over time wither and fall apart. You can see here that this building has kind of weathered and fallen apart over time, which is just the natural way of things. If you don't put energy into maintaining a building, this is what you get over, 50, 60 years, which isn't even really that long. The same thing happens if, you stopped eating food. Eventually your body's going to shut down and we wither. Also, if you want to take something and create order, aka organize something, like my room, right? If I have my room is super messy and my clothes are all over the floor, I'm going to have to put energy into creating order. And that's sort of the relationship here. Things will naturally fall apart over time. So it doesn't really take energy to go from a solid or something that's organized and complex to something that's less complex. So reactions that are going from complex to less complex, that's pretty natural, and it's going to release energy and heat into the environment. Sometimes that could be really slow, like our abandoned building, or it could be really fast with the use of things called enzymes inside of our bodies. So we actually take sugar and break it from complex to less complex, aka sugar into carbon dioxide, and that releases energy and heat, which is why we are giving off heat right now. And the energy we get is in the form of ATP. You can see here in this reaction, we're going from a glucose to the carbon dioxide. It goes from complex to less complex, which is going to release ATP, and heat is going to be lost as well. So if you want to go from less complex to more complex or chaos into something that's organized, that is going to take energy to happen. Just like I said before, if I want to clean up my room, it's going to take energy from me. If I want to take Lego pieces that are scattered throughout the floor and click them together into some sort of structure, I have to use energy to do that. So those types of reactions are actually going to absorb heat and take energy to go from that less complex state to more complex. So going from less complex to more complex is going to require energy input into that system. And this is not going to just happen naturally. You don't see things magically building themselves. Everything that gets built or goes from less to more complex has to have energy, and it has to have something that provides that service. So in nature, the big example is plants can take carbon dioxide, less complex, and build a sugar using energy from the sun. So that's the energy input. So what the plants are doing is they're taking that sunlight and basically converting it into chemical energy. And that energy is now going to be stored in the bonds of this glucose, which is going to have a lot more potential energy and be a lot more complex than our carbon dioxide. We're going to elaborate way more on this when we go into photosynthesis in particular. This is not the full equation for photosynthesis. We're going to also talk about cellular respiration as well and get more into those particular processes in completely separate videos. This is just sort of laying the foundation. So that pretty much sums up the relationships between photosynthesis, cellular respiration, the laws of thermodynamics, and the basics of energy.